Hi, my friends. It has been a long time from last video, as you know, and tonight I decided to make a new video about the last subject. And at the last class, we talked about the closed systems and the analyzing of the closed systems and energy balance equation, etc. And I wanted to make a video for my foreign friends. And after this subject, after closed systems, we will talk about actually open systems and steady flow systems, as you can know, turbines, compressors, etc. So let's take a look at this question. A mass of 15 kilogram of air in a piston cylinder device is heated from 25 degree to 77 degree. Sorry for actual quality of the video, but this is my best I can do. And by passing current through a resistance heater, and the pressure inside the cylinder is held constant at 300 kilopascal during this process, and a heat loss of 60 kilojoule occurs. And determine the electric energy supplied in unit of kilowatt hours. Okay. And in case of any misunderstanding, I prepared a sketch here. As you see here, we have air, amount of air in a piston cylinder device, as you see here, and we have Q loss, heat loss we have, and electrical resistance here. And after we supply voltage, a current will pass through this wire and through this resistance and make, as you can actually, how can we say, um, create a heat actually. Actually, this is voltage input. Sorry, voltage input. Work input, yeah. And it is actually asked us to find electrical energy supplied by this voltage, this electrical circuit. So we can say that here we have work input, actually electrical work as an input. Yeah, work input. So as you can remember from actually energy balance equation, general energy balance equation, what we had is, as you can remember, for a closed system, actually Q input, isn't it? Q input, then work input and mass input, and minus Q output, heat loss, isn't it? Yeah. And minus work output, any work that we gain from the systems, and minus mass output. Yeah, mass output. And this term is directly equal to this term equals to the energy change of the system, as you can remember, the energy change of the system itself. And as you can remember, the energy of the system consists of uh, internal energy change, kinetic energy change, and potential energy changes, isn't it? And because we don't have any brief actually about the velocity and altitude for the calculation of the potential energy change and velocity for the kinetic energy change. So we can directly say that instead of delta E system, we can directly write delta U, isn't it? The internal energy change. Okay, so let's analyze. Does we have any Q in? It is obvious we don't have any Q in through the system, isn't it? We have work input, which creates uh, which creates heat and makes the air inside the cylinder warmer, isn't it? But this is not actually directly set as Q in. So we cannot say there is Q in for this system. Okay, this is zero. We have working. Yeah, this is the electric work. So we can say, yeah, we have working. No mass input because this is closed system. No mass input, no mass output. So there is also uh, zero mass output there. Okay. And does we have Q output? Yeah. This is written. This is given in the question as 60 kilojoule heat loss occurs. Okay. This amount is 60 kilojoule. Okay. So yes, we have Q output and work output. Yeah. This is tricky. Why is tricky? Because when we have actually current through this wire, and this wire, this resistance makes heat, okay, and this heat will actually boost the air temperature, and when air becomes warmer, and this piston cylinder device, because the system is iso bar, which the pressure is actually constant. The pressure does not change. So we can say that the system isobar, isn't it? The pressure doesn't change. So due to this fact, the piston, when the air gets warmer, piston uh, uh, starts to move upward, isn't it? So there is also what? There is also we have boundary work, isn't it? Boundary work as a workout. Okay, we have what? We have boundary work. Okay, so lastly, what we have is work input, which is electrical work plus, sorry, minus, yeah, minus Q out minus boundary work equals, we can directly say that delta U, isn't it? Delta U. No, here work with boundary. Yeah, this is the last relation we have. So you can recall from previous chapters when we sent work boundary next to the delta U, what we had finally, what we had, let's write it. We have delta U here, sorry, let's write here. Delta U plus, plus boundary work. What was the boundary work is P times delta V, isn't it? Pressure times volume change. Let's say that this is volume and the volume change. What this summation gives me is delta H, isn't it? Yeah, enthalpy change, enthalpy change. So I can directly send this work boundary, sent next to the delta U, and finally we will have is electrical work minus Q out equals to delta H, isn't it? Yeah, enthalpy change. So actually it is important to know what is kilowatt hour, isn't it? What is kilowatt hour? So uh, let's analyze here, okay? Let's open a window here, okay? So what is kilowatt? Kilowatt is, let's say here, kilowatt is kilojoule per second, isn't it? Yeah. And I can write kilojoule in terms of kilowatt as kilojoule equals to kilowatt second. Okay, kilowatt second. And let's make this kilowatt second kilowatt hour. Okay, can we convert this to kilowatt hour? Yeah, directly we can convert. So let's again write kilojoule equals to kilowatt times second, and it is important, 1 hour, 1 hour is 3600 seconds, isn't it? Yeah, and seconds are cancelled, and consequently what we have is kilowatt times hour over 3600 kilojoule equals to kilowatt hour per 306 sorry, yeah, 3600, isn't it? So um, I will obtain a value in this equation in unit of kilojoule, and after that I will multiply it by 3600, isn't it? So the electric work electrical work is not known, so it is actually asked to us to know, and work electrical work minus Q out. What is Q out? Is 6 kilojoule. 6 kilojoule. Okay. 6 kilojoule. Uh, then delta H. What is delta H? Is actually we can use the constant specific heat method here, and which constant specific heat is actually used here. Actually, because the system is isobar and the pressure is constant, we can use Cp value, isn't it? Cp value for the air in room temperature condition, in a room temperature condition, is equal to what? Is equal to, sorry, 1.005 kilojoule per kilogram Kelvin. Okay, kilojoule per kilogram Kelvin, 1.005. Okay, and what is the temperature difference? The temperature difference, actually it is not necessary to convert these degrees to Kelvin. Okay, because whatever the units, actually the temperature difference does not change. Okay, so 77 minus 25. Okay, so 52, isn't it? 52. Yeah, 52. Actually, you can say Kelvin. It doesn't matter because Kelvins, isn't it? Kelvins are cancelled each other here. Kelvins and Kelvins. So here we have kilogram, and I can, because I cannot do any scalar actually process. I cannot actually proceed because here we have kilojoule per kilogram. Here we have kilojoule. But I don't know. I know the mass of the system, mass of the air, 15, isn't it? I can actually multiply this term, the right hand side term, by the mass itself. So what we have, work electrical work minus 60 equals to 1 point. Let's do this. 1.005 kilojoule per kilogram times the 52, because cancelled, the kelvins are cancelled, 52 times the kilogram itself, mass, isn't it? And the consequently we have what? We have 783.9 kilojoule, yeah, directly, yeah, kilojoule. And here we have 783.9 kilojoule. Here we have 60 kilojoule. When we actually send the 60 next to this term, and when we sum them, let's say plus 60. What I have is 843.9 kilojoule. Okay, we have that. So uh okay, what we actually find is 843.9 kilojoule, and I figured out here when I divide when I divide kilojoule by 3600, it will give me what? Kilowatt hour, isn't it? Kilowatt hour. Okay. When we do this division, uh, I will convert kilojoule into the kilowatt hour. Okay. So when I divide this term, because it is kilojoule in unit of kilojoule, when divide this term by 3600, okay, it will give me what? It will give me kilowatt hour. So what is the result is, sorry, 843.9 over 3600. It will give me, and actually approximately, yeah. Why it is not seen? Okay, approximately it will give me, as you see here, point two, point two three, we can say 4, and it's enough. Yeah, kilowatt hour. Okay, that's all for this question. Thank you for watching. See you.